welcome back to the YouTube channel. So I know I've been away for some time, 3 months or 2. Well, that's because I have started my degree and I have some activities that I'm involved in uni, so I didn't really have time. But now it's semester break, so I'm gonna do my best and discuss as many questions as I can to help you all out for your physics paper, of course. Yeah, so without further ado, let's get started. Today we are looking at 9702 paper 22, which is basically paper 2, October-November 2025. So this is actually a very recent paper, last year's paper, by the way. Yeah, so we look at question 2 from this paper. Okay, so a spacecraft in deep space uses jets of hot gas from its thrusters to change its velocity. Figure 2.1 shows a side view of the spacecraft and some of its thrusters. Okay, so we have thruster C here, thruster A here, thruster B here, okay. And they've given you the center of gravity. That's nice, okay. And then they said thruster A is a distance of 1.6 meter leftwards. 1.6 meter leftwards, okay, from the center of gravity of the spacecraft. Thruster C is a distance of 0.4 meter upwards from the center of gravity of the spacecraft. Thruster A and B can produce forces on the spacecraft in the upwards direction only. Thruster C can produce a force on the spacecraft in the leftwards direction only. Okay, we need to highlight this. Produce force on the spacecraft in the upwards direction. Thruster C only can produce in the leftward direction. All the thrusters shown produce forces entirely in the same plane at the center of gravity. Okay, just now we got see that thruster is a distance of 1.6 meter from the center of gravity, and C is 0.4 meter upwards from the center of gravity as well. Okay, now let's look at what the question wants us to do. A Roman 1. Thruster A is activated, producing a force of 60 Newton upwards. Thruster C is also activated, producing a force of 220 Newton leftwards on the spacecraft. Calculate the resultant moment due to these forces about the center of gravity. Okay, so did you realize that they didn't give us thruster B's force? Because they want to find the resultant moment about the center of gravity. If you realize, this is the force of B, they said upwards, right? A and B upwards. So the line of action of force from thruster B is actually coinciding with the center of gravity, it coincides the center of gravity. So since it coincides the center of gravity, if you want to find your distance from the center of gravity, it's actually 0, because your line of action of force is coinciding with the center of gravity. And F times D by your F times 0, because the distance is 0, you're going to get 0. So your moment for B will be 0 about the center of gravity. Okay, now we know that the thruster A has a force upwards, and they said just now is 60 Newton upwards, and C has a force of 220 Newton leftwards. So now let's do this. Let's set direction first, okay? Clockwise as positive, anti-clockwise or counterclockwise as negative. Okay, so resultant moment is basically sum of all the moments. Clockwise, which is clockwise? Ideally, if you look at it, this is supposed to be clockwise. This is supposed to be anti-clockwise, right? So clockwise is 60, 60 and your distance is 1.6. Perpendicular distance. So this question is actually really nice. They actually give you all the distance on your own. And even though they give, you should also check if your forces and your distance are perpendicular to one another. Because that's one of the rules that we need to follow. The force has to be perpendicular with the distance. Okay. Then minus, why minus? Because it's going to go anti-clockwise. 220 and the distance is 0.4. So if I get my calculator, I will get 8 Newton meter. So my answer is 8. And this is basically 8 Newton meter clockwise. We can write at the bottom here also. Resultant moment is 8 Newton meter clockwise. Yeah. So if you're gonna ask me, right, is it possible if I set my clockwise as negative, my anti-clockwise as positive? Yes, it's 100% doable. As in that it's possible you can do that, but your final answer you're going to get as negative. You should get negative because you set your negative as clockwise, right? So if your final answer you get negative, that's okay. Just write something like this down there and say that resultant moment is 8 Newton meter clockwise. Make sure you visibly write this, that your clockwise is negative, anti-clockwise is positive, so that the marker that sees it, they knows, oh, why did you get negative and what does your negative indicate. Your negative indicates clockwise, okay, and it is clockwise, then it's fine. You are good to go. Okay, so make sure you denote your direction first. Okay. Now, Roman 2. State and explain whether the forces from A and C are a couple. That's very cute. Okay, anyways, are a couple. Okay, so forces A and C, which is 60 Newton and 220 Newton. Okay, before we answer the question, we have to understand what couple is. So we know couple has to have the same magnitude of forces. That's your first rule. Second rule is you have to have it in opposite direction. And your third rule is your resultant force has to be 0. Okay, so let's go up and look at it. First rule is magnitude of forces must be the same. Are the magnitudes the same? No, clearly 60 is different from 220. So we couldn't get the first one right. Then let's check the second one, opposite direction. Are they in opposite direction? Not really. One is going upward, one is going to the left. Clearly they are not in opposite direction, right? So no. Resultant force has to be 0. Of course not, because for resultant force has to be 0, the forces has to act in the opposite direction. Clearly it's not even in opposite direction. One is up and one is to the left. So there is a resultant force. It is not 0 because they cannot cancel each other out. Like I said, because it's not in the opposite direction. If it's like this, okay, it makes sense. You can cancel each other out because they're in the opposite direction. Given the fact they're also in the same magnitude, like 60, 60, then yes, you can cancel each other out. The resultant force is 0. But in this case, one is upward, one is to the left, and you are not even in opposite direction. You are also not the forces with the same magnitude. Therefore, the resultant force is not 0. So fails everything. Hence, is it a couple? No, it's not a couple. So you write, no forces A and C are not a couple as the forces are not doesn't have the same magnitude. It's also not in the opposite direction, and resultant force is not 0. Oopsie, resultant force is not 0. Resultant force is not 0. Okay? Yeah. Why did I say just now? Because not in opposite direction. You can't cancel each other for it to be 0. Yeah. So that's about. So they say state and explain whether the forces from A and C are a couple. You state it's not a couple and you explain. Given the fact it's 1 mark, actually, you just say it's not a couple, you get 1 mark, and you explain why. One explanation, you get another mark. So this is actually like 3 mark explanation. Yeah. So you can actually just stop here and you're good to go actually. Yeah. Well, of course, it's always good to write more and not less, but it's good to write more as long as you're within the line, then that's fine. If it's over the line, they're not going to read it right away. Yeah. So conclusion, they are not a couple. Okay, so let's move on to B. Thruster A and C are now switched off and the spacecraft is stationary. Thruster B is activated at time t1, producing a constant force on the spacecraft until the field runs out at time t2. Okay, very important point, a constant force. As the field is used, the total mass of the spacecraft decreases, and they want us to sketch the variation of speed of the spacecraft with time from t1 to t2. Okay, now what we know is about the constant force and the mass is decreasing. So if I write the formula F equals to ma, my force is constant, my mass is decreasing. Therefore, to ensure my force is constant, my acceleration has to increase. And we know the gradient of speed against time graph is actually acceleration, because s over t, speed over time, the change in speed over the time interval gives you acceleration, right? So we know that the speed versus time graph, the gradient gives you acceleration, and we know that acceleration is increasing. Therefore, we have to draw a positive increasing gradient graph, which is something like this. Yeah. So if you're wondering why I did not draw a straight line, because this is constant acceleration, not increasing acceleration. It's like a constant acceleration throughout. It's not the increasing acceleration graph. If they say the mass is constant, not changing, then yes, because your force is constant, mass is not changing, therefore your acceleration is also constant. However, in this case, they did say the mass of the spacecraft is decreasing. Therefore, you should draw a positive increasing gradient graph. Okay. So this is the correct graph and this is the incorrect graph. Alright, okay, now we will move on to C. The spacecraft now splits apart into a carrier and a payload as shown in figure 2.3. Okay, during the split, an average force of 5,500 Newton acts on the payload for a time of 0.36 seconds. The velocity of the payload increases by 8.5 meters per second in the upwards direction. The combined mass of the carrier and the payload is 2.5 times 10 to the power of 3 kg. So what is nice about this question is all the units are in SI unit. Like none of it is like in gram or like cm per second or millisecond. It's just nice, all of it is in the SI unit, so you can do your calculation cleanly. So first question, state the principle of conservation of momentum. Okay, so this is something that you should know before you enter the exam hall. All these basic definitions you should know. It's a free marks for you actually. So What is it actually? So principle of conservation of momentum is actually the total momentum before equals to the total momentum before collision, you can say. Before collision, total momentum after collision. If no external force acts on the system, or you can say for an isolated system lah, or for an isolated system. Or you can also say, instead of saying total momentum before collision is equal to total momentum after collision, you can say that the total momentum of a system is conserved or is constant if no external force acts on the system, or you can say for an isolated system lah. Yeah. So another way you can write is, okay, I'll just write another color. Another way to write this, oh my god, why the color is too bright? I write this is the total momentum of a system is constant. Then you continue for an isolated system. It's very important to say for an isolated system or no external force. Yeah. And also very important to say the word total. You can say total or you can say sum, any synonym, as long as it gives the same meaning. Yeah. Okay. Got your 2 marks already. Now, show that the mass of the payload is 230 kilograms. Okay. Do we have information? Yes, we definitely do. We have a force here. We have the time here. We have the change in velocity here, because they say increases by. Keyword is by. That means the change, it increases by 8.5. I mean the change in velocity, final and initial, is 8.5 in the upwards direction. Okay, so I can think of 2 ways to actually do this, but both of them are actually very similar ways. It's just how you look at it. So the first way is using F equals to ma. That's first way, which is a bit indirect because you have to sub in your V and your T inside your A. Another one is using this formula, F equals to m V minus U over T. So if you realize, this part is actually the same as this, right? Because this is acceleration, change in velocity over time. So it depends on how you look at it. So in a way, both is the same. You can use any of the ways depending on what you see first. Okay, so I'm just going to use this way. Okay, so using method 2. In exam, you don't write like this, okay? Then you say using method 2. I'm showing you 2 different methods. You don't give examiner choice later to let them choose your working. You pick one and do. Here I'm just showing you there's 2 different ways to compute it. Okay, so F you know is 5,500. Your M is what you're going to find. Your change in velocity, they say increases by 8.5. That means it's 8.5. Let me write copy here. 8.5 is my 8. Okay, 8.5 over time interval is 0.36. Take out your calculator, calculate your mass. You're supposed to get 0.36 divided by 8.5. 232.94 kg. Round it up to 2 significant figure is 230 kg. So, there will be times where your final answer is not exactly what they want. It may not be exactly, but bear in mind that when you round off to 2 significant figures, you must get the same answer. If you cannot get the same answer, then you need to check back your working. Yes. So, your final answer, when you get here, it may not be exactly 230. It can be any value, but like I said, as you round off, you must get the same value. out of the 2 or 3 significant figures based on the question, you must get the same value. Yeah. Okay, so we have shown that. The last part of the question, Roman 3. Calculate the magnitude of the change in velocity of the carrier. Just now we calculate for the payload, right? This is the payload, we got the mass. Okay. We can actually use principle of conservation of momentum here. Okay. How? So we know total momentum before and after. So before, mass of carrier I'm going to put as MC. Then initial velocity of carrier I'm just going to put as UC. Then plus mass of payload, initial velocity of payload, mass of carrier again, final velocity of carrier, plus mass of payload, final velocity of payload. Okay. So what I'm going to do now is I'm going to group all the carrier terms one side and group all the payload related terms to one side. Okay. So now let's do that. So I'm going to group carrier terms here. MC, initial velocity, so you can factor out your mass. Okay, I'll explain to you why am I grouping like this in a while. Okay, wait, let me write this up. Okay, now what you're finding is this. This is what you're finding. This is what you want, the change in velocity of the carrier. Do you have the mass of the carrier? Yes. Where is it? They gave you the combined mass of the carrier and the payload to be given is 2.5 times 10 to the power of 3. And you got the mass of the payload. So you take this minus this, you will get your mass of the carrier. So you have that value. You have mass of payload, which is 230. And what is this? This is the change in velocity, which we know it is 8.5 here. So when you look at this question, right, I know you might be wondering that, okay, how do I find the initial velocity? How do I find the final velocity of this payload and this carrier? Before you even think of that, you look at what you did in the previous questions. So in the previous questions, you find the mass. How did you find the mass? Using the change in velocity. The change in velocity is given by 8.5. So find a way to form an equation that can make you use the change in velocity that is given in the question. So in this case, change in velocity, we know it's final minus initial. And they say that the velocity, the question here, of the payload increases by 8.5. That means you take the final minus initial velocity of the payload, you should get 8.5. Because they say increases by 8.5. So this thing is 8.5. You have the value. So you have all the values here to find what is your change in velocity of the carrier. Okay. Now let's do it. Okay. Mass of carrier, the combined mass is 2.5 times 10 to the power of 3 minus 230. Oops. UC minus VC equals to 230 8.5. Okay. So it's better you put a bracket for this. Okay. 2.5 times 10 to the power of 3 minus 230 gives me 2270 UC minus VC. This makes our calculation easier because they straight away ask change in velocity, and you do have a change in velocity term here. So which makes your final answer to be obtained easier. Yeah. 230 times 8.5 is 1955. Okay. As usual, do your algebra. You should get 0.86. Okay. Here is something that you have to be careful. Change in velocity usually, okay, it's final velocity minus initial velocity. Right, that's how we were looking at it, like here, final velocity minus initial velocity. In this case, initial minus final. So the right way to actually interpret this is actually write this as negative VC minus UC equals to 0.86. So VC minus UC is actually negative 0.86 meter per second. Don't forget your unit, 0.86 meter per second. Okay. Now check and see in your question, does this make sense or not? Okay, you go up. This is your payload. This is your carrier. Does it make sense that your change in velocity is negative 0.86? Negative means downward, right? And your carrier is moving downward. So it does make sense that your change in velocity is negative 0.86. Yeah. Okay. You got that already. Now, the question asks you for magnitude only. So since the question asks you for magnitude, you can omit the direction and just write 0.86. Because they only ask for magnitude. So, it's fine. You don't have to take it into consideration. Okay. Yeah. So, actually that's about it. That's the entire spacecraft question actually. So it's a mixture of a little bit of moment, then a little bit of application of your formula and understanding what is acceleration, how does it relate to speed, then comes principal conservation of momentum. Yeah. So that's all for today's video. I hope you get to learn something new, maybe a different approach to this question. And I'll see you in the next one. Make sure to take care of yourself and stay hydrated. Bye bye.